now. All right, so we have section 3-4, increasing, decreasing, and the first derivative test. All right, so when we left off with 3 notes, okay, we could find the absolute extrema. Did the derivative, found the critical numbers, and then we plug those values in to figure which one was highest, which one was lowest. All right? As you probably noticed on some of the examples, sometimes the critical number did not give you a maximum or minimum. Okay, it was just in there somewhere. Okay, so today we'll answer a couple of questions. Which critical numbers correspond to local extrema? All right, and then how can I tell all of this without even looking at a graph? Okay, so first off, let's look at that definition. Okay, should be an easy definition. Okay, we put in here just to formally define it, but basically it says a function is strictly increasing on interval if for every numbers in that interval, if one of them is less than the other, then the y values are also one less than the other. Okay? Should make sense. If I got x here, x1 here, x2 here, all right, what is the y value? It's bigger than that one, yes? Okay? And any time on this little interval right here, that's going to be true. Okay? Decreasing is just backwards. If I take any interval, or any points inside of an interval where it's decreasing, all right, then if I plug the y value, x values in to get y values on that interval, that second y value should always be lower than the first y value. Okay? Increasing goes up, decreasing goes down. All right, if we look down here, we can see a graph. All right, and they've drawn some tangent lines for you. Okay, look at this first interval, those tangent lines are what? Increasing. They're positive, right? Here, where it's decreasing, those tangent lines are negative. Okay? And you can see that throughout there. So that brings us to the next little theorem. Okay, kind of gets us to how can we tell without looking at a graph, without plugging in a whole bunch of values. All right, if a function is differentiable on an interval, all right, then what this says is the derivative is bigger than 0, and the function is increasing. If the derivative is less than 0 for everything in that interval, the function is decreasing. Okay? So, derivative is positive. That means, hey, slopes are going like this, so it's increasing. Derivative is negative, slopes are decreasing. Going there, I wasn't on the video for that one. Oh well. Example, find the open intervals on which f of x equals x cubed minus 1.5x squared is increasing or decreasing. Okay, without even looking at a graph. So, first thing we're going to do is take the derivative. All right, can we take the derivative of this?
Yes.
All right, what is the derivative of x cubed?
3x squared.
3x squared. All right, the derivative of minus 1.5x squared minus 3x. Okay? So, there's your derivative. Okay, just like last time we could find critical numbers. Find critical numbers by setting what? Setting equal 0, very good. Alright, so what can I factor out of both out of those terms?
3x.
3 and an x, yes? That would leave me with an x for the first term and a minus 1 for the second term. So my critical numbers here are going to be what?
0
and 1. 0 and 1. Alright, so what happens on those critical numbers is that's going to be boundary points. We'll see this in a little bit as well. Alright, so on my number line over here, I went ahead and drew one out for us. This is our first derivative number line. Okay, I'm going to put a number 0 for my first critical number and a 1 for my second critical number. Alright, and I'm going to choose some test values. Okay, I'm going to pick something that's in the interval that's less than 0. For example, -1. Alright, if I plug a -1 in to the derivative, you need to plug it into the unfactored form or the factored form, doesn't matter. Factored form probably easier. Okay, so if I'm doing the factored form, go ahead and write those factors out here to the side. If I plug a negative into 3x, I get what?
-3.
Negative 3. I get a negative, yes?
Yeah.
If I plug a negative into x minus 1,
Negative.
I get a negative. And those are multiplying, so negative times negative is positive. All right, so what that means is in that interval between negative infinity to 0, my derivative is always what? Positive. Therefore, in that interval, my graph is doing what? Increasing. So I'm going to draw a little line that's going up. All right, now I'm going to find something between 0 and 1, like 1/2. All right, the exact values are not important. It's just whether they're positive or negative. So if I say 1/2 times 3, I get 1.5, which is positive, right? 1/2 minus 1 would give me, so overall it's going to be, so the function is doing what? Decreasing. And then something bigger than 1, like 2, plug it in, 2 times 3 would give me positive, 2 minus 1 would give me, so overall, so the graph is increasing. So if I wanted to write this answer out, okay, I would say this function is increasing on what intervals?
Negative infinity to 0. And then 1.
All right, and we use parentheses on increasing and decreasing. Okay. And then decreasing here, our only interval that it decreased was what? 0 to 1.
Business said we did that,
We did some of that whole number line test stuff in algebra. Okay, we just didn't do it the first derivative because we didn't know what that was. Okay, we did this a lot when we were trying to figure out inequalities, figure out where it's greater than. But we would do it with the original function, not the derivative. All right, a good connection there. All right, a little definition here for us. Okay, it's not in our book, but it's in another book. You might see it on the AP test. A function is strictly monotonic. Okay, mono meaning 1. All right, like Mr. Peanut from Planners has the monocle. Little eyeglass he wears is one of them. Okay, it's a monocle, 1. Okay, or your relationship should be monogamous. Means you're with one person. Okay. Look at you, Katie. All right. All right, it's strictly monotonic if it's either increasing or on the entire interval or it's decreasing on the entire interval. Okay, so for example, this first one over here, f of x equals x cubed, this is strictly increasing over the entire interval. Okay, it's got this one point here at 0 that has a tangent line of 0, but it's only an instantaneous spot. Everywhere else it's increasing, so we call this one strictly monotonic. Okay, strictly increasing. All right, this function over here, while it looks pretty similar in the graph, between 0 and 1 is actually what? Constant. So this one would not be strictly monotonic. Okay, because there is an interval over which it is constant. It's going up, then it's constant, and then it's what? Going up. Okay, this one only has an instantaneous spot. And if you were to do the derivative, what's the derivative of x cubed?
3x squared.
3x squared. All right, and so now no matter what number you plug into that, if I plug a negative number into that, it's going to be what? Positive. Positive number is going to be positive. So it's strictly increasing because the derivative is always greater than or equal to 0. All right, next up we have the first derivative test. Okay, we probably could have gleaned this from the first example. Okay, but the first derivative test says if a function is continuous on an interval, that's important. If not, then it all falls apart. Okay, you got to do some steps. Okay, take the first derivative of the function. We've done that before. Might find the critical numbers, and I just put in here the definition of critical numbers in case you need to be reminded. Those are numbers that are defined in the function but make the derivative 0 or undefined. Okay? Sometimes it might make the function or the derivative 0 or undefined, but it's not in the function to start off with. That's probably going to be an asymptote. Okay? And then you're going to set up a number line just like we did with the critical numbers as boundary points. Okay? And I guess I should put in here, because we do have those weird cases where a number makes the derivative 0 or undefined, but it's also undefined in the regular equation. All right, we also want to include those. Okay? So pretty much not with just the critical numbers, all right, but whatever makes the derivative undefined or 0. That's what you're going to put on your number line. All right, you'll choose test values just like we did, figure out increasing and decreasing. All right, and these last two parts say, hey, if the derivative changes from negative to positive, that means it goes from decreasing to what? Increasing. Then what's going to happen there at that critical number? It's going to be a minimum. Okay? And if I go from increasing to decreasing, what's going to happen at that point where it changes? It's going to be a max. Okay? All right, and that actually tells you where the minimums and maximums occur. To actually find what that local extrema is, you got to plug it back into the original function. So let's look at example 2 I have there for you. All right, find the local extrema of 2x cubed plus 9x squared minus 24x minus 10. All right, now thrown the standard graph. If you were to stick this in your graphing calculator, okay, you can go ahead and do that now while I'm talking. Okay, if you stuck it in there at zoom 6, your regular zoom, this is what it looks like. All right, we can tell it's going up for a while, but then we lose it for a second. Then it comes back down, we lose it, and then it does what? Comes back up. All right, so we can kind of tell where they're going to be. Somewhere 1, 2, 3, 4, 5, 6, somewhere between 0 and negative 6, and somewhere in between 0 and like 2. All right, but we don't see the whole graph there. Okay, we could zoom out. We could try to zoom out. Okay, but we can actually let our calculus figure out for us quicker than that. Okay, so let's do it. If I want to find the local extreme, step 1, find the derivative. All right, this one should be easy because it is a polynomial. All right, so the first one gives us 6x squared plus 18x minus 24. All right, find the critical numbers. So we need to set this equal to 0. All right, what can factor out of everything? 6. That'll make the factor in that quadratic trinomial easier. So x squared plus 3x minus 4. And this gives us what? X
Plus 4
minus 1.
All right, so our critical numbers are negative 4 and 1. All right, I guess we need to make sure that those actually work in the question. All right, they do because it's a polynomial. All right, but when we set up our number line, we've got negative 4, we've got 1. All right, my factors, I've factored it out. I'm going to write to the side. X plus 4, x minus 1. Just kind of helps me figure it out. Possibly could do it without writing those there. All right, and then I'll choose some test points. All right, something that's less than negative 4. Negative 5. If I plug a negative 5 into x plus 4, I get a negative 1. Negative 5 minus 6 gives me negative 6. So negative times a negative is positive. So I know between negative infinity and negative 4, the graph is going up. Okay, the derivative is positive, so my graph is strictly monotonic in that section. It's going up. All right, between negative 4 and 1, I'm going to choose
0.
If 0 is there, choose 0. That will give me a positive times a negative, which is negative, so I know I am decreasing. Yes. And then finally, something bigger than 1, 2, which will give me, which tells me I'm going what? I'm increasing. All right, so at -4, my derivatives tell me my graph goes from increasing to decreasing. So I'm going to have a local what there? Local max at -4. All right, and to figure out what that value would be, I need to plug that back into the original problem. All right, and I'd probably use my calculator, honestly. Okay, you can do it without, but it's going to take you a while. So do that quickly for me. 128 plus 36. Not 36.
58.
Give you
That
50,
was 4 times.
gives you what? 102?
I got
102.
All right, so our local maximum occurs at -4, and it is 102. All right, what happens at +1?
It's a local min.
It's going to be a local min because it goes from decreasing to increasing. So we have a local min, which is f of 1, which that should be easier to do. 2 plus 9 is 11. 11 minus 24 is -13. -13 minus 10 is what? -23. Yes, ma'am.
What if there's no difference? Like, what happens if you can't find a local maximum?
It might not happen. Okay? Great question. If this was negative and then it still remained negative, then this would not be.
So it'd just be a maximum.
It would just be a maximum. Okay? For example, on this problem right here, all right, you'd have a critical number at 0. All right, but to the left it's going up, to the right it's going up, so there's not a local extreme in here, even though there's a critical number. Okay? Because I believe it was Fermat's theorem that said, hey, Fermat's theorem says that if you have a local extremum, it's going to happen at a critical number, but it didn't guarantee a critical number gave you the local extremum. All right, and so now, if you actually wanted to see the whole graph in its entirety on your calculator, you could change your window accordingly. You could realize that I need to go down how far from my y min? -23. I'd probably go a little bit lower than that, maybe -30. And then above 102, maybe 110, 120. Let's see the whole thing. All right, I think I actually, on this one, threw it on there for us. I went from -50 to 125.
That's the derivative.
That's the actual function.
Wait, so is it?
Okay, this was the original function. Okay, but this is the viewing window -10 to 10. So I don't see all this stuff up here. Because I found my local max and local min, I knew exactly where those y values were. I changed my window to go down and up so that I could see everything. All right, let's try this one. Trig. You love trig, right?
Yeah, sure.
All right, find the relative extrema of this one. I guess I should note here, because this is a new word maybe for us, the word relative
Your uncle.
and the word local are synonymous. Okay, some textbooks use relative minima, some of them use local. Okay, they're the same thing. All right, so what's the first step?
Find the derivative.
Find the derivative.
0.5 minus cosine x.
Times 1.
Technically, if you want to make it a
If you wanted to say-
chain rule, but yes.
I want a 2-0.
All right, now we set this equal to 0. I'll get you.
Greedy.
All right, so set it equal to 0. And then I can do what with a 0.5?
Bring it.
Subtract it over, which will give you negative 0.5 is equal to negative cosine. I can get rid of the negatives by dividing. So basically, where is cosine 1/2? All right.
Power over three.
Pi over 2.
Yeah, pi over 3.
I want
Pi
power
over
over
2.
two.
Yeah.
I was gonna say power.
All right. It's going to be pi over 3. Okay. That's one of the places. Where else is it?
Negative pi over 3.
No.
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 One.
2 pi over 3.
Two power over three.
It's the one down here.
What?
What? 5 pi over 3.
All right. It's going to be 5 pi over 3. Okay.
Because
It's going to be in our first quadrant because cosine is positive over there, and it's going to be over in the fourth quadrant. Which, yes, it is a coterminal negative pi over 3, but in this interval 0 to 2 pi, that is 5 pi over 3. Okay, so we have pi over 3 and 5 pi over 3.
Can I bring a circle for the test?
No. You can memorize it.
seriously need to memorize.
You did that last
Every
year.
day.
You had to memorize things for football competition.
I mean, do you have a copy of the alphabet whenever you go to English class now?
Do you really need one?
I have to say it.
I feel like
That's a good question.
It's not the same thing, Mr. Woolman. It's one I've been using for like 17 years. The other one has
17.
All right, so for my first derivative test, I have a first derivative number line over here. Okay, if you're taking an AP test on a free response, make sure you note that out because there is a second derivative test, which we'll learn later.
Oh,
Okay, so make sure you show that out. I see the eye rolls back there. All right, so let's plug in something less than pi over 3.
0.
Okay, 0 is at the very, very end of our interval.
Oh.
Okay.
1.
So I guess technically, yeah, we're going from what, 0 to 2 pi?
So,
0.1.
All right, so pi over 3, I would use like, what's an angle less than pi over 3?
Pi over 6.
Pi over 6, right? Or pi over 4? All right, if I plug that in here, okay, cosine of pi over 6 is square root of 3 over 2. All right, so if I say 1/2 minus the square root of 3 over 2, is that going to give me negative or positive?
Negative.
Square root of 3 over 2 is bigger than 1/2. So if I say 1/2 minus the square root of 3 over 2, it's going to give me. All right.
I'm sorry. I don't want
If I have 25 cents and I subtract 50 cents,
and then you get it.
I'm going to have what? A negative 25 cents. So negative, so it's going down. All right, between pi over 3 and 5 pi over 3, pi over 2. Okay. Several angles I could do in there. Anything in between these two. All right. Well, pi over 2, cosine of pi over 2 is 0. 1/2 minus 0 is positive half. So it's going to be increasing there. And then something bigger than 5 pi over 3, we have maybe
11 pi over 6.
11 pi over 6.
Oh.
Okay, that's
You
a.
use pop?
Oh, we don't want to use 2 pi because that's at the very, very end.
No, just like.
Not bigger.
That's in between.
So you got to make sure you choose some things that are in the right place, interval. So 11 pi over 6. Well, cosine of 11 pi over 6 is the same thing as it was at pi over 6.
So that.
So square root of 3 over 2. So 1/2 minus square root of 3 over 2 would also give me.
Wait, what are we doing right now?
Probably the relative extreme.
So
The local.
at pi over 3, the graph goes from going down to going up. So what happens there?
It's a minimum.
Yep, we have a local or relative min. Okay, at f of pi over 3. And we can plug that in and get an answer. I'm just going to leave it as it is right now.
Oh,
It's not going to be a pretty answer. It'll be, what, pi over 6 minus Square root of 3 over 2. All right, local max is going to happen what? 5 pi over 3. So we have local max at f of 5 pi over 3. Okay, and we can plug those back in to figure out exactly what those y values are. But I'm good right now.
So we're not gonna put the y in.
We could. We could. If we really want to, this is going to be pi over 6 minus the sine of pi over 3 is the square root of 3 over 2. All right, and this one will give me 5 pi over 6 minus the square root of 3 over 2, except, let's see, it actually would be plus, because sine will be negative down there and negative, yes. So, all right, let's look at this one. Okay, same thing. First thing we do is find the first derivative. This is going to be a chain rule, however. So this will give you 2 over 3 cube root of x squared minus 4 on the bottom. All right, because 2/3 minus 1 is what? Negative 1/3. So cube root on the bottom of that stuff on the inside. All right, and then because it's a chain rule, take the derivative of the inside, which would be what? 2x. So really the top becomes 4x. All right, critical numbers. All right, what makes the derivative of 0?
Nothing.
Undefined.
All right, derivative of 0 in the top 0, right? So as we get 0 from the top. All right, what makes the derivative undefined is whatever makes the bottom 0.
Zero.
2.
And
Negative 2.
2 and negative 2.
So what makes the top 0 and what makes the bottom 0?
Yes. What makes the top 0 and what makes the bottom 0? Top is 0. Bottom is whatever makes this root 0, which will be 2 and negative 2. All right, so we do a little number line. We got negative 2, 0, and 2. All right, we start plugging some stuff in. Something less than negative 2. Negative 3. All right, that would make the top what? Negative. The bottom, we have 3 times the cube root of x squared minus 4. That's always actually going to be what?
Positive.
It's always going to be
Negative.
positive.
Oh yeah, because of the squares.
That's always going to square it, and minus 4 is always going to be, well, not always positive, but negative 3 would square it. 9 minus 4 is 5. 3 times the cube root of 5 is positive. So overall, it's what?
Negative.
Negative, so it is decreasing right there. All right, something between negative 2 and 0.
Negative 1.
Negative 1. If I plug that in the top, I get negative. If I plug into the bottom, I have negative 1 squared, which is minus 4, which is negative. Cube root of a negative is?
Imaginary number.
All right, square root would be imaginary. Cube root, I can actually do it. The cube root of a negative is going to be a negative, so the bottom is negative. So overall, it's positive. So it's going to be increasing. If I plug a 1 in, the top's going to be positive. Bottom is going to be negative, exactly the same as we just got through doing. Okay, 1 squared is 1. 1 minus 4,
3.
negative 3. Cube root of a negative 3 is going to be negative. All right, and then finally something big. Oh, so overall it's what?
Negative.
So it's decreasing. And then what happens at, say, 3? We get positive on top and positive on the bottom. Because 3 squared would give you 9 minus 4 is 5, which is positive. So it's going up.
So it's 2 minimum.
Yes. We got,
There's 2 minimum and 1 max.
all right, so we have a local minimum at f of what? -2. If I plug a -2 in, -2 squared is
4.
4 minus 4 is
0.
0 to any power is
0.
0. And we also have the same thing at what? 2,
2.
which if I plug a 2 in, I also get
0.
0 on this one. And then our local max happens at 0, right?
Yeah.
All right, so that'll be a -4 to the 2/3 power, which would be what?
Oh, what?
It's still negative.
Oh, what is it?
Negative.
What was it?
Negative
again?
2.5.
Negative 2.5.
Should give you approximately 2.5.
Yeah. Negative.
It's going to give you a positive.
Why?
All right, if you take a -4 and raise it to the 2nd power, you get 16. And the cube root of 16 would be 2 square roots of 2, which you said was approximately what?
2.5.
Okay, again, that is -4 to the 2/3 power. And the way I would work that out is -4 squared is 16. So we get the cube root of 16. Oh, 2 cube roots of 2, my bad. Alright. 2 times 8 is 16. 8 comes out as a 2. Alright. What that graph actually looks like, it looks like this. Okay. Alright, because what happens at -2 and 2, the derivative was what?
Wait. Whoa.
At 2 and -2, we found those critical numbers by making what? Bottom 0. So notice the derivative is undefined. We got a cusp there. And then at the top, 0, we have tangent line of 0. So it's pretty up there, cusp on the sides. All right. Let's take a look at this one. All right, find a local extrema. If you're all watching the video, you might want to pause it right now and work it. But then we're going to work it right now, straight up. So pause it. All right, we're back. All right, so taking the derivative of this would require the quotient rule, low D high minus high D low over low low. So low.
X squared. 4x cubed. Is it
Minus
x 4x cubed?
All over x squared.
All over x to the 4th.
Over x fourth. I guess you could do that.
All right, if we clean up the top, that's going to give us, let's see,
4x to the 5th minus 2x to the 5th plus 2x. Well, minus 2x, my bad. All over x.
which I could say this is what? 3x to the 5th minus 2x all over x to the 4th.
Hold on. You made a
That's
mistake.
4x to the 5th.
It's 4x to the 5th.
4x.
2x?
There you go.
Be very careful. So 4x to the 5th minus, give you what, 2x to the 5th?
Yeah.
All right, and then we can clean it up even more before we start working with it.
Take out the 2x at the top.
All right, you can take a 2 out.
Wait.
All right, and you can take an x out.
So it'd be x
All right, I'll do it. 2x, which will give you x to the 4th minus 1 all over, which you could cancel out and become 2 times x to the 4th minus 1 all over x to the 3rd. All right, so critical numbers. What makes the top 0?
One.
And?
2. No. 0.
And negative 1.
1 and negative 1. All right, what makes the bottom 0?
0.
0. Is it a critical number?
No.
No.
No. If you look at the original problem, can you plug a 0 into the original problem?
No.
Mm,
No, makes it 5. But then it just
And then squared on the bottom.
Oh, no.
Because they'll be undefined.
All right, it's plugging a 0 is undefined in the original problem. So 0 is not a critical number, but we do need to include it in our number line. Okay? So 0 is not a critical number, but we do need to include it on our number line. So we got -1, 0, and 1. And I might put me an X through the 0 on my number line just so I know there's not going to be a local min or max there. Okay? All right, and then we start plugging in some values. We plug in -2, -0.5, half, and 2. All right, and then let's see if I can remember what that problem was. It was what? 2 times x to the 4th minus 1 all over x cubed, correct?
Yes.
So we plug a -2 in. The top is going to give you positive. The bottom is going to give you
No, negative, sorry.
negative because it was to the 3rd power, right? So
Oh.
-2.
X cubed.
Oh, you plug into the. I'm plugging the wrong way.
Okay. You can, if you plugged it into one of these up here, then the top you have to worry about more. Okay, but if you look at the very, very bottom, the last one, top positive, bottom negative, so overall negative, so it's what? Decreasing. If you throw a -1/2 in, -1/2 to the 4th power is going to be a positive fraction, but -1 would give you negative. Bottom, since it's negative cubed, will give you negative. So overall it's positive, so it's going up. If I plug a 1/2 in,
Positive fraction.
Wait.
it'll be a negative on top divided by a positive on the bottom.
Negative.
So negative overall, so it's going down. And then the last one's going to give you.
Positive.
All right, so to finish this problem up, okay, do we have local minimums?
Yeah.
At -1 and at 1, do we have a local max?
Yes. Oh wait.
No, it went from positive to negative, but there was a what? Undefined there.
Why is it that doesn't work like
All right, because if you plug a 0 in here, it's undefined.
Oh yeah.
And so what that graph actually looks like, it looks like this. So yes, it goes from going positive to going negative, but there's an asymptote there, so there's no local. So we got local mins at f of -1, which would give you what?
Let's see.
2, I believe, and f of 1, which would also give you.
Oh, no.
Plug it back into the original problem.
When is
Oh my gosh.
So it'd be
-1 to the 4th would be 1, plus 1 is 2. -1 squared would be 2. All right, so we had one problem we didn't get to. We can look at that later.
yeah.